So we'll go with it. So today I'm going to be talking a little bit about thermal considerations. And at the end of this, as mentioned, I'm going to recap on lab number 1. So what thermal considerations mean is a lot of this is cooling electronics. So this is sort of basic heat transfer stuff. Basic heat transfer more in how we might need to use it as engineers, not sort of the theory behind the heat transfer. Just if we have a device, we need to keep it below some temperature. How do we figure out how we do that, what the temperature should be of the device, what considerations are there. To do this, we'll use something called the thermal resistance. From that, we can calculate the heat rise and select an appropriate heat sink. So this stuff should be very similar to a lot of what you've seen when it comes to electric circuits. So there's a nice parallel here that makes it really easy to use. So the beginning part of cooling electronics. And if you do it wrong, bad things happen, things blow up or catch fire. So there's a lot of sort of, we're going to go over some really basic examples here. It can get a lot more complex, and there's some pretty interesting books on areas of cooling electronics. And one of them is called like something, hot air rises and heat sinks. Everything you know about cooling electronics is wrong. But as an example, if you freeze ice cubes, does anyone know what freezes colder, cold or hot water? Hot water, yeah. And this seems totally insane, right? But it's it doesn't work the other way. Hot water boils faster than cold water. It's not some weird, parallel universe of physics. But it's called the Mpemba effect, and in 1963, there's a student making ice cream at his school. To make ice cream, they boil milk, put sugar in it, and freeze it. There's only so much room in the freezer, so being clever, he says, well, I'm just going to put my ice cream in hot, because I don't want to run out. If you're one of the suckers at the end, you don't get to make the ice cream. So you're supposed to let it cool and then freeze it, but he didn't listen to his teacher. So he put it in first, and his froze earlier than others. At the time, he asked his physics teacher, or his teacher, like, whoa, what happened? Mine was in first, and it froze first. And they just told him he was wrong. They said, oh, no, you probably stole someone else's, or something like that, right? Anyway, so he eventually repeated the experiment himself a bit, and, it came up, and he asked his physics teacher, what's happening here? What explains this? And he just continued to mock him, basically, and said, oh, that's Mpemba's physics. That's not real physics. It doesn't make sense. And I guess he would use this throughout the class. If people got stuff wrong, he'd be like, oh, that's because he used Mpemba physics to get that answer. So not very nice, but this is sort of what he was up against. People thought it was so silly. Eventually, he asked a visiting professor. The professor just had his, some lab guys do the test for him, because he was like, okay, well, I'll test it and see what happens. The lab guys reported that, actually the hot water did freeze first, but don't worry, we'll keep trying this experiment until we get the right result. Eventually, they sort of realized, actually, no, this is the right result, and they came up with this graph. So I don't know if you can quite see in the bottom, but here you have initial temperature. So this is 20 degrees Celsius up here. It takes about 100 minutes to freeze whatever size they're using. If you heat it all the way up to 80 degrees, you can see it's taking about 30 minutes to freeze. So it makes a drastic change. And there's sort of a lot of reasons for this, but the point is that for some of this thermal stuff, there is a lot more going on than this really simple thermal resistance we're going to use. The thermal resistance is a really good way to get estimates to spec parts. But at the end of the day, the proof of concept is a lot more important. So doing a really simple test than whatever your basic assumption you're making is. So that's sort of an introductory story to show you why proof of concept is a lot easier or more important than just making assumptions about how something will work and just going with that forever, when you can easily test it. All right, so when we talk about heat transfer and what sort of, all this freezing stuff is heat always flows from a hot surface to a cold surface. So when we're cooling electronics, or cooling a device, the device is dissipating power. It's trying to shed that heat to the colder air. So your car engine's shedding heat to the colder air, your laptop to the colder air. If the air around it's warmer, there's nothing it can do. It can't, the heat will go the other way. The warmer air would warm your device. And that can occur in three different ways, and it's really the first two are the only ones we care about. So conduction is where we have physical contact. So you have your stove, 4 burners. And when you physically put your pot on the stove, it's conduction that's transferring heat from your burner onto the pot. So this is the physical connection. Convection is where we're transferring heat through a liquid. A liquid in this case often meaning air, basically. So in convection transfer, we have a hot device on a circuit board, just sitting there, and it's going to naturally shed some heat into the air around it. If it's just sitting there, it's called natural convection. It's just whatever the heat that's coming off it. As an alternative, we can also put a fan across it, a little crappy fan, and we can blow air, and then we can have what's called forced air convection. So this is another area, and forced air convection normally means we're shedding heat faster because we have that air movement across it. We also have radiation heat transfer, which is if you had a hot surface, in a vacuum or something like that, it's actually going to transfer heat by radiating it outwards. So this isn't going through the liquid, like the air or whatever we have. This is actually just radiating. We don't really care about this for electronics normally. In terms of cooling electronics, you do care about it for other things. Or if you're doing a spacecraft, you might care about it. But for what we're talking about, it's such a minor amount of heat transfer, we're going to consider it irrelevant to our estimates. And this class and this lecture and what I expect you to use is all about estimating heat transfer to estimate, how much power can I roughly dissipate without blowing this thing up. So the type of heat flow you might see in real life is you have a heat dissipating source. So at the bottom we have this rectangle, and this is if you've built a computer or something, this is a chip, say maybe your CPU in your computer. So something that's generating a lot of heat. To increase the amount of heat that we transfer, what we do is we mount what people call a heat sink on it. And heat sink sort of gives you the wrong idea. It makes it sound like magically it takes the heat and just sends it out. But all the heat sink does is it has more area. So the CPU, just has an area of whatever this length times width is, and often a square. Whereas the heat sink has all this additional area because of all the valleys here. So it has a much larger surface area. And that's all the heat sink is doing, is increasing the surface area of the chip to give it more area to dissipate the heat out. And there's a few sort of different aspects of the heat transfer. So what you have is we have the chip, we have the heat sink, and there's actually often some sort of interface between them. Be air or be some other surface. And you can see this, why we have this additional thing, is we have an example here. So this is flipped upside down, but this is like your chip CPU. This is your heat sink here. The surface of them is not perfect, so there's little microscopic gaps. If you want to get better heat transfer, if you just have air in here, what you have is you don't have perfect conduction between the two. There's a bit of convection between the heat sink to the air, then the air back to the package case. Or the package case to the air to the heat sink, to that backwards. So if we could put a material in there that joins these two sides, this will improve our heat transfer because we can continually have the conduction heat flow. And so what we can see in this diagram is you can assume that there's in fact another small, you can just call it a surface in between. So this is the sort of problem we face. We've got a chip, we've got something, and we have a heat sink. For most of the work we're doing, all of the problems can be broken down into a series of a heat source here. And then we have a number of items, and then we kind of have air, which is where the heat's going. So we have the heat source, and we can represent everything in between with just resistors, which you know. So we have a heat source. So in the previous example, we had the gap. Oops. We had the gap between the chip surface and the heat sink. So this is, for example, the heat source again. And this is the chip temperature. We then have some resistance, what we're calling thermal resistance. And then we have the temperature at the other side of whatever that is. So this is, that little layer of material we're putting between the chip and the heatsink. And then we have, for example, so this we could say temp at, you could call it heatsink bottom. And then at the other end of that, so we then have a resistance representing the heatsink, so we now have the air temperature. So at the end of the day, we have the heat source, which is the chip. We have some thermal resistance. We have the temperature of the heatsink bottom, which will be a little lower because of this thermal resistance. And then we again have the air temperature. So this is the model we use. And we like this model because it's very, it has a lot of parallels to how resistors in electric circuits behave. So if we have a bunch in series, we just add the resistance to generate an equivalent model of the entire system. So we could represent this just by one resistor. If we don't care about everything in between it, that can be our complete model of the thing. And we can say, how much heat are we dissipating? Let's figure out the temperature rise. All right, so let me give you an example of what those calculations are. The calculations are given, let's just take one simple item. So again, there's two temperatures on each side of this item. What I'm calling this is, the small surface in between here. Temperature 1, temperature 2. And in the previous diagram, I had sort of a resistor representing the two sides. There's T1 on one side, T2 on the other. And conductive heat transfer has this equation at the top, where the amount of heat that we have can be calculated based on, there's what's known as the thermal conductivity, or you also see it written as the thermal resistance. But the idea is this shows you how much heat, the temperature will rise for a given heat and area. So that's this constant here. We have the area of the surface, so whatever this area is here. And we have the thickness of the surface, so however thick it is. So given that, we can calculate the change, or calculate the amount of heat that it represents based on the change in temperature. Obviously, we can easily rewrite this to give us the change in temperature based on the amount of heat. This is the more useful one. Based on the amount of heat we're dissipating, the constant, and the thickness. So going back to this example where we have a CPU and a heatsink, and this gap in here with filler material. If you've sort of built a computer or something, there's different examples of this filler material. So if we have a CPU here, and I have one here, CPU base, I have two choices. I can put on, whatever this heatsink compound is, this filler material. And again, this material, the whole objective of it is to just fill this gap in here. And you can buy some that's really cheap, in a big tube that looks like toothpaste tube or something, although probably would kill you if you brushed your teeth with it, so do not recommend. And you can buy other really fancy compounds. So this one has silver in it and stuff. And there's all sorts of stuff that'll claim, but the basic idea is they have this expensive version and cheap. And they'll say, well, the expensive version has way better thermal characteristics, so you should use that to avoid blowing up your computer and stuff like that. And it's true, they do have a lot better thermal conductivity. So the simple one, if I use the example of this zinc oxide, this random white stuff here, the zinc oxide one, it has this thermal conductivity 25.2. The other option is, say we use the silver, and you can see the thermal conductivity is 20 times higher than the zinc oxide option. And if we go back to that equation, so you could say that's 20 times better, which is accurate, and that's what they sell you on. It is 20 times better, that's true. The problem is that, so if we go to this equation, and what they're telling you is that, we can rewrite this, so change in temperature is equal Q divided by all this stuff, so you end up with T over Ka. And they say, well, because this K is now 20 times better, your change in temperature is going to be 20 times lower than with the other crappy stuff that's really cheap. So we can go through and see what sort of change in temperature that would represent. As an example, I've picked a Q, so this is the power dissipation of 50 watts. From the CPU, that's sort of just a generic figure. Obviously this will vary a lot depending on the CPU, but say we had to dissipate 50 watts of power. The problem is that if we take this equation, we plug all the stuff in, so we have 50 watts here. We have the thermal conductivity here. So I'm using the number for, oh wait, that's not the thermal conductivity, that's the thickness. So this is the thickness of the layer. So I'm saying this layer is 0.2 millimeters thick, which is a fairly reasonable guess. You can look up what sort of thickness layers you end up with, but it always ends up around that level. So 0.2 millimeters. We have the thermal conductivity number here. So the thermal conductivity. And then we have the area of the CPU. So I've just sort of guessed if it's 3 centimeters squared. That's what the area ends up being. So that was just a total guess, but it's all fairly relatively accurate. So the problem is that at the end of the day, there's only 0.4 degrees Celsius temperature change between the top and bottom of that layer of thermal paste. So what this means is that, if we had our CPU like that, we have our CPU here, so this is way exaggerated in size, and then we have this thermal paste layer in the middle. Because this thermal paste layer is so thin, it actually ends up making almost no difference. So if our CPU here is at 50 degrees Celsius, the other side of it will only be 49.6 degrees Celsius. So it makes very little difference what paste we put in there. So the really expensive stuff is in fact 20 times better. That's completely accurate. But the only difference is rather than being at 49.6 degrees C, it's at 50 degrees C. And it won't make a lot of difference, or 49.9. It probably ends up being closer to degrees C. So it won't make a whole lot of difference whether you use the really expensive stuff or the really cheap stuff. It's basically the same in this case because the thickness of that layer is so small. So these sort of thermal equations help us answer questions like what sort of devices do we need to specify, what sort of heat transfer, heat sinks, the heat transfer pads, and stuff like that. So let's go back to this. And the other thing you can see is that if you look at what the thermal compound, sort of how the improvement is in thermal resistance, you can see, if you just had dry conditions here, there's a curve, and the thermal compound greatly reduces it. So there's the dry conditions is the one curve, the thermal compound is here, And then there's another option. There's a special sill pad or isolator pad. So these pads actually are used as well for electrical isolation, which we'll talk about. But you can see it's much, much worse. So there's certain cases where going from an isolator pad to the really fancy thermal compound would make a big difference. But that's not the same problem as going from the cheap thermal compound to the expensive thermal compound. So that's just one example of a heat transfer equation. So as I mentioned, if we want to calculate the whole system, we're going to represent everything as that resistance. And this is what avoids us having to do, this calculation to figure out the temperature at each stage. We can just generate a equivalent thermal resistance for the whole system. One thing that's important to note is, so when you look at a data sheet, and the assignment will go through an example of this a bit, or you'll have to do an example of it. I'll do one now. We'll have a bunch of stuff. So in this example, what we have is 3 thermal resistances. And for example, we care about the junction to case is saying we have a device. Try a device here. And this is going to be like a transistor or something. Internally, inside it is what they call the junction. So this is where the silicon device is. And so we can call that the temperature of the junction. Oops, that should be a little J there. So what we care about is the thermal resistance between that junction and the outside of the case, because we can't measure that junction temperature, but we could, for example, put a probe on this case here. And so we have T case. And using the thermal resistance, if we know the power dissipation of the device, we can calculate, well, based on the case, I know what the junction temperature is. There's a few caveats about that. One of them is that the given values are going to be valid for a very, very specific environment. And hopefully the datasheet will tell you that. They may or may not, depending how in-depth the datasheet is. But to sort of give you an example of that, I have 2 resistors here. So these are resistors in what's called TO220 package. And this is the same package that you have the MOSFETs are in. So you'll see this package in the lab. And all I've done is I've taken 2 of them. One of them is mounted vertically, as you can see here. One's mounted horizontally. And the horizontal mounted one is also a little closer to the desk, which will impact it a bit. And I can put a fixed amount of power through each one. So I have a power supply, and you can see it's putting 1 watt effectively of power into each one. The minuscule difference between this it ends up being like 0.1 Celsius temperature difference, which we wouldn't care about. So each one has 1 watt of power in, so you could, in the equation say Q equals 1 watt. And once it's stabilized, so you let it run for a while and then you measure the temperature of them. The vertical mounted one is running at the case temperature, so this is TC, is 78 degrees Celsius. In the other one, TC equals 83 degrees Celsius. And this is solely due to the vertical mount of this case actually gives you a small amount of current. Oops. So when the device, if I sort of look at the side of it like this, there's a big metal pad on the back. As it heats up, the hot air is going to rise, and that actually generates a small current. And this convection current has a little bit of airflow and helps the device cool. So even though it has one single number in the data sheet, it just says, let's go back, 62.5, even something like which direction you've mounted it in could fairly drastically affect it. In this case, it's just a small effect, but it will depend on the package quite a bit. As a side note, the junction to ambient, if you notice from the data sheet, the thermal resistance in that case was spec'd as 62 degrees or 62 Celsius per watt. So you expect the temperature rise to be 62 degrees Celsius for every watt that the device dissipates. And that was the junction to ambient, I believe. Ambient. So what we can see here is that I'm passing 1 watt through it, and there's about a 60-degree temperature difference between the outer case and the ambient temperature. So that is about what we expect, because you notice the background temperature is around 20 degrees Celsius. So the 20 degrees Celsius plus 60 should give you somewhere around 80 degrees Celsius. So that shows you that these, as a very ballpark method, are able to tell you what you expect case temperature to be based on the amount of power you're dissipating and the ambient. Again, everything's about temperature differences. Oops. Where do I have that? So everything's about the difference in the temperature or heat. Nothing's absolute. So in this case, it's saying it'll be 62 degrees higher than ambient. If ambient's 20 or if ambient's 40, it doesn't matter. It's just going to be that offset.
Are those values in that table, those RF data values, is that basically Ka over T?
Yes. So if you go back, I guess sort of T over Ka, I guess, right? Would that be? Because in this case, so yeah, if you just have K, that's just the thermal conductance, so that requires the area and thickness. Their thermal resistance just needs the power, right? So you don't need any of that stuff. It's sort of simplifying it for you. Which I think in the assignment they have this. So yeah, so these will be thermal resistances in the assignment. I think there's a typo there. I need to check. I'll tell you in a second. As another example of this, I've taken that exact same package and mounted it in 3 ways on the circuit board. So we have a device just soldered to a circuit board. We have a device sort of pushed over horizontally on the circuit board. And this device is soldered. There's a closer up photo of these. It's pushed over and soldered, so it has a much nicer sort of thermal connection. And if I do the same thing, so I put a watt through this resistor, what you see is that the package temperature is now 64 degrees Celsius, whereas with that same vertical mount before, it was 78. So it's 14 degrees, cooler, and I haven't done anything differently. I've just put it on a circuit board, which is how I'd use it in real life. I wouldn't just, have it floating, doing nothing. I'd have it mounted. What's happened is on this circuit board, this whole top part and the whole bottom part is a big copper pore. And this copper pore is actually helping the heat is conducting to the copper pore, and then through convection radiates outwards into the environment. So this changes the thermal resistance of the entire system. And how, the effect of this will depend on the size of this copper pore, how the device was mounted. It could be if there's just a copper pore on one side. In this case, I have it on both sides, but the bottom side is pretty close to the copper. So there's a whole range of variables here. So again, that's why these are useful as a sort of rule of, rough rule of thumb. If you want to get more accuracy, you're going to need to figure out what is the total system thermal resistance. And for the other two, I have this example where I've pushed it over. So you can see there's a small air gap here. It's not bolted down. It should be bolted down to minimize that air gap. I have not done that. I've just been lazy and pushed it over. In this one, it's soldered down completely, so there's no real air gap. It's all a continuous metal connection. And sort of as you expect, the one that's the continuous metal connection is much cooler. Again, these both all have 1 watt going through them. So you can see the surface of this guy is at 60 degrees Celsius, whereas the surface of this other guy was at 71 degrees Celsius. You'll actually notice this is worse. The best thing to do, between This guy and the one where I pushed him over is actually just to leave him standing up because he's vertical. He gets that nice convection current, and this helps to dissipate some of the heat. In the case where I've pushed it over, because I may think like, oh well, it's got this this mounting tab, but I don't have a bolt or something. But it'll be pretty close. I've actually gone worse. So I've gone from 64 Celsius to 71 Celsius, and it still has the full copper pore. So it still has the connection through the pad to everything here. But because I've eliminated, I have this really small air gap that very little air will flow through. I've made the situation even worse than if I had just left it standing. Obviously, the best thing to do would be to have this connection to the back pad or to have heatsink. But between the three of them, that shows the differences.
Right.
Yep.
In that picture on the left, what is around the chip?
Oh yeah, sorry. That's I forgot to mention that. So that's an artifact of the thermal camera. They don't. The silver areas have very low emissivity. It isn't accurately measuring anything that's reflective. So that's also why on this photo, the metal tab is actually hot, much hotter than even possibly than the case. It doesn't show up that way. So I just have a really cheap thermal camera. If you have, I'd say real ones, that you can use for this, you can set the emissivity of the device to compensate for that. So yeah, that's a good point. It's solely an artifact of the system that this is hot, just as hot as all the other stuff. It's just reflecting, instead of measuring it, it's reflecting the temperature above it. So, any other questions on that stuff before? Okay, so I'll do an example heat rise calculation. This will be similar to what's in the assignment. I'll make a note on this. I just realized in the assignment I have some of these thermal resistance values, but the units are wrong. So I'll post a fixed version, but just so you know. It doesn't affect, the numbers are right, it's solely the units that I have the meter, inverse meter, and inverse Celsius. It should just be inverse Celsius. So an example heat rise calculation. We have a voltage regulator, and this is one of the parts in your kit. An LM7805. So what this chip does is it takes in some higher voltage and outputs a fixed 5 volt. So the idea is that you have this device, you put in 12 volts, you get out 5 volts. Sort of magic. One of the sort of caveats of this is what's known as a linear regulator. And if you have, I don't think I have. Yeah, so if you have this is how you might use the device in a circuit. So LM7805. You have your output, and let's say we just connect it to a resistor. There's some load. We don't care what that load is. If you have 1 amp going through that resistor at 5 volts output, this device draws in basically 1 amp of current. So you'll see it's very inefficient because it's going to have to waste a lot of excess power. So that 1 amp in is at 12 volts, or whatever your voltage is. The device itself can theoretically operate up to 35 volts of input. So you might say like, okay, great, I can put in whatever voltage I want at 1 amp and get out 5 volts at 1 amp. Which, just quickly reading the data sheet, you might think. So there's a bit of a trick in here, and that's that the input power, so if you remember, power is current times voltage. In this case, you have 12 watts of input power, and power out, so power in, power out equals 5 times 1, 5 watts. So you have 5 watts of output power. So most of the power, 7 watts of this power, has actually been just totally wasted. It's been thrown away because that's how the devices work. So it just dissipates 7 watts of power. So it does a very good job of heating, dissipating this power. And this is what you have to be careful of when you use the device, because it otherwise might say, like right at the beginning of the data sheet, output current in excess of 1 amp, which is true as long as you don't fry the device by exceeding the junction temperature. So it has some limits on the junction temperature, which we can see is, in this data sheet, it says something like 150 degrees Celsius. Typical for most semiconductors is 125 Celsius. As soon as you go above that, even temporarily, the device is destroyed. So that's what you never ever want to exceed when we're doing these calculations. So let's look at, yeah.
Do the devices underperform high temperature?
Pardon?
Do the devices underperform?
So do they perform worse at the higher temperature, you mean? So basically at that temperature, do you mean if you exceed the temperature, does it just perform worse?
Almost maximum.
So yeah, they do. There will be some specifications, so it will depend on the device. They're built, if you look in the data sheet, it'll basically give you a spec, and often the specs will say, whatever it is, so voltage regulation, it'll say from minus 20 to 50 or 70 Celsius, it's this one value. Over a wider range, from minus 40 to 125, it'll say plus minus 2% instead of plus minus 1%. So as the temperature goes up, it depends a lot on the circuit, what type of device it is, if it performs worse or not. Or
it's a CPU. If it's at 20, it's at the same as CPU at 7.
Yeah, so in that case, you have the CMOS. This is a really simple linear regulator, so it doesn't have any issues. There's no switching in it. With the CPU, you have issues where your the ability of the device, how quickly it can switch, is drastically affected by temperature. So that's because of the CMOS devices in it. For this, it's a solely linear part. It does perform differently, but not as much. But yeah, for a CPU, you want to get it colder because you can run it faster. Some devices will be like that, some won't. You should have to see the data sheet. So, other question?
Yeah. Technically, for this specific device, if you're at 69 degrees Celsius, would you need a heatsink or anything?
If you were at what, sorry?
If we're at 69 degrees Celsius, we wouldn't have to worry about heat sinking. If you're not at 71, we would.
So that's, it has this operating temperature range. This is a very generic, it's just guaranteeing things will operate in this range. The only thing that really matters is the junction temperature. So if your device, the question was that, it says this 0 to 70 Celsius, what's the deal with that? Because if you're at 71, we all of a sudden have to can't use this device at all. So in that case, the real answer is that it depends on the junction temperature you have to calculate. So I think they're just trying to give some leeway. A lot of the times devices will vastly underspec, just to say we guarantee it to operate in these conditions. It may well be usable outside of these conditions. This is what overclocking CPUs people have done forever. But no warranty. So
TA was like a noise parameter.
there may well be.
Because for amplifiers, it gives that TA's operating temperature, determines how much noise you have in the sound.
Okay, so that's there's a whole other thing involved in that. That's the amount of noise. The amount of noise you generate will depend on the temperature because there's a sort of temperature noise component to it. In this case, all we care about, we don't care about that at all. We're just looking at when will the device blow up. We don't want that. So yeah, there's a whole other aspect of this, and this is also the same, cooling electronics problem is relative to that because it might be you need your amplifier to only ever get to 30 degrees Celsius, or you may need to cool it, and you can use these same sort of calculations. All I'm using is, don't blow it up, and that's the maximum junction temperature. So, okay. So what this would mean is we need to do a heat rise calculation. So in this case, the data sheet actually gives you, just out of interest, for a given ambient temperature, so this is the bottom, you can sort of see it goes from 0 degrees Celsius, 25, 50 degrees Celsius, 75. It's telling you, if you have no heat sink in the device, how much power you can dissipate. So this is the axis, this axis here is how much power we can dissipate. I already calculated I'm going to be dissipating somewhere around 7 watts, which is telling me it's well above the level with no heat sink. It's saying you can only dissipate a few watts of power. As the ambient temperature increases, that the amount of power we can dissipate drops even further, because it means the temperature rise we have less sort of margin between what the maximum TJ junction of 150 degrees Celsius and what the ambient temperature is, because it's that difference that's killing us. If we add a heatsink, so it just pulls out a random number from them with some heatsink, 10 degrees Celsius per watt heatsink, we can dissipate more power. And then it goes up at the top. You know, if you had an amazing infinite heatsink that could dissipate all the power, theoretically, you could almost take up to 20 watts the whole time. So I don't know why they tell you that. That's not a super useful figure, but I guess if you want to dissipate more than 20 watts, you know, it's impossible. In between here, sort of the no heatsink and infinite is where engineering comes in to figure out what you actually need. As a side note, when they say ambient, they of course mean the temperature right around the device. Why that matters is if you have something like, you know, if you have the device in a box, so this is a side view. So in the middle here, this is my LM7805. And it's in a box, you know, outside the box, it might be 30 degrees Celsius. But what the ambient temperature is what it is right outside the device. And right outside the device, it might be a lot hotter because you have this device dissipating heat into the box itself. So in that case, ambient would be 50 degrees Celsius. So for something like this, what you would have to figure out is what is the thermal resistance, you know, between the box and that device, which you can either simulate or just test to figure it out. So you have to be sort of careful about what is ambient. For everything we're doing, not a problem because it's all going to be sitting in front of us. And you don't have to worry about that. But a lot of the times you do want to put stuff in the box to look nice, and you have to be very careful with that. In that case, what you might do, for example, is you have that device actually connected to the case or connected to a heatsink on the case such that ambient can become the outside air that you know the temperature of. So if we're doing this calculation, we might have an example like, you know, we have some different heat sinks we could choose. And we know we want to do this, dissipate that 7 watts, but which of these heat sinks can we use? So there's different costs. You know, it's in quantity 1,000. And some of them are even designed to be used. So this has a spec that's specifically designed to be used with a fan. So then we may have to say, oh, do we even need a fan? That's more cost, more complexity to add in. You know, rather than just trying to pick one randomly and hoping it's the best, we want to figure out what will actually work, what's the minimum size we need. So I'm going to use I picked a different data sheet, a different device that had, for example, it says the junction temperature the maximum junction temperature is 125 degrees Celsius. So it says that somewhere. So everything's guaranteed over from, you know, negative 40 Celsius to 125 degrees Celsius. To answer the previous question, in this example, they had some spec that was specified at, you know, if the junction temperature is 25 degrees Celsius, here's what we guarantee. And there was a line under this I didn't include in the cutoff, but it said if it's, you know, from minus 40 to 125. The output voltage isn't as stable. So the data sheet will also tell us some figures we need. I'm just going to use the simple one, junction to air, or junction to case and junction to air. So these are the thermal resistances that we sort of saw before. And again, these are pulled right from the data sheet. And any data sheet you look at will have various figures like that. So I can say, well, I desire junction temperature of 100 degrees Celsius. So if I need a junction temperature of 100 degrees Celsius, we use our formula and say, well, there's the junction temperature. And what I care about is the case. So this is the case around the device. And so therefore, I need the thermal resistance between the junction and the case, not junction and ambient, because we're going to deal with ambient in a second, which is 5 degrees Celsius per watt. So for every watt that passes through it, there's a 5 degree temperature rise. So we can just say, well, I need the case to be at 65 degrees Celsius. And I know this because when it dissipates 7 watts, we have this 35 degrees Celsius temperature rise between the junction and the case. I told you I want the junction to be at 100 degrees Celsius. Therefore, the case is going to have to be at 65 degrees Celsius. When the case is at 65, I know the junction is at 100. So what about the heatsink? So this is the second part of our little, diagram. So if I draw this again, I had the junction. Oh, go back, sorry. I had the case here, was at 65 degrees Celsius. The junction was 100 degrees Celsius. And over here, I have the ambient temperature. And I'm going to tell you, well, I want the ambient temperature to be as high as 50 degrees Celsius in the worst case. So 50 degrees Celsius. Therefore, the temperature difference across the heatsink has to be 15 degrees. And when I say temperature difference, what I mean is when we look at the heatsink specs, they all give you this number, this 3.1 degrees Celsius per watt. This means if the device dissipates 1 watt of power, there's a 3.1 degrees Celsius difference between whatever the point is the device mounts, wherever they've tested it, so right there in this example, and the ambient air. In this much smaller heatsink, you can see that if 1 watt of power is being dissipated, there's a 28 degrees Celsius temperature rise between the ambient air and that package of the device, or where the device mounts. So that's the figure we need to figure out. And all we do is we divide the temperature difference, so that 15 degree difference, by how much power is being dissipated, and we need this 2.14 degrees Celsius per watt. Is the spec. So that's the heatsink we need. That's the answer. And you can go back and say, okay, well, which of those heatsink options? It would actually be bigger than the one that I pulled up there. So you could either select a bigger heatsink, add a fan, or you may go back and say, okay, well, that maybe I was a little, extreme in my spec, so I'm going to change it, and I'm going to say, actually, I only need, I'm only going to run this up to 30 degrees Celsius. So I'm going to change my assumptions. Or you could say I am going to allow the junction temperature to get up to 125. I previously scaled it down. In that case, the temperature rise of the heatsink becomes 35 degrees Celsius because we've reduced the maximum ambient operating temperature. And we now only need a 5 degrees Celsius per watt heatsink. And if you go back, you can see, okay, well, that's something I can do. This middle guy would definitely work. I could use the other one with a fan, but this guy, there's not a chance it would work, because that's saying the temperature rise is going to be 28 degrees Celsius per watt. So if I'm dissipating, 7 watts through that thing, the temperature rise will be insane. It won't be reasonable. All right. So that's very, very quickly how you do these thermal calculations using the thermal resistance. And again, all it is you're given some degrees Celsius per watt rise, and we just go through and we can say, okay, well, on one side to the next, there's the temperature difference based on the power being dissipated. For the next section of the circuit, here's the next section of the temperature difference. So we can chain that together to, form between the body of the device, some in-between system, be it, that gap filling material, and the heatsink itself. And that helps us decide, how much power to dissipate, what sort of heatsink to use, and the operating temperature that the device will work over. So, the other sort of important thing to note, and you'll see this, is a lot of devices have the tab as powered. So I have two examples, LM7805 and LM7905. One's a positive, one's a negative voltage regulator. The tab in one is electrically connected to ground. The tab in the other is electrically connected to the negative input voltage. What this means is that, if you had one big heatsink and you were trying to mount both these devices on it, you're going to have a dead short, because this tab that you're mounting, sorry for the bad diagram here, in one of them is connected to ground and one of them is connected to an input voltage. You don't want that. So there's these electrical isolator pads. In this case, what we have is rather than that gap filling material, we have this little pad here. And so here is the heatsink. You know, this is the heatsink here. Here's the little pad. And this forms an electrical barrier between the ground, the tab, and the heatsink itself. Obviously, you also need this little plastic washer here. Because otherwise when you put the bolt through, the bolt would also touch the tab, and that would be bad. So that electrically isolated washer fits into the hole on the tab. So you can see it sort of fits in right there, and gives you some electrical isolation for the bolt. So it's just something to be aware of when you're looking at adding a heatsink to a system. Question, yeah?
Is that the curve? Is that this top curve for the heatsink graph?
Which one, sorry?
Is that the top curve for the graph?
Way back. Yeah, so this was, you're paying attention. Way back, these are not as nice, you'll see, because if we go all the way back, where was that? Yeah, there was this graph showing you what the thermal resistance was for various options. So dry conditions was nothing, just jamming them together. The compound was when we add, one of these, expensive compounds on them, and this isolator pad was that pad I just showed you. Because the isolator pad's so thick, because it's also generating electrical isolation, we end up with a much worse thermal resistance, but you don't have a choice sometimes. You might need it to prevent a short in your system. Or you can try to make your heatsink hot, which is it electrically has power on it, but that might not be a great idea. All right. Questions? Let's keep going. So, yeah, electrical isolation. Requires electrical isolation. Yeah, and just the note that you can do these calculations similar to voltage drops across the resistors. So before we move to lab 1, any questions on any of that stuff? Okay, very quickly, lab number 1, if you didn't look at it, what we're going to be doing is driving a motor. So at the beginning of the motor driving lab, I showed you how if you connect a power source to a motor and then disconnect it, you'll get these big spikes. So we're going to experiment and try to see those spikes. We're going to add the diode across it to block them out. So these labs are done in your groups, by the way. And then you'll add a diode and try to suppress it and graph that on the scope. In part 2, I'm giving you a schematic for an H-bridge. You're given these devices. You'll have to look up the data sheets. There'll be links. There's links in the lab. The lab's on BD Learn too as a PDF, by the way. And you'll sort of have to figure out how to solder this together. If you haven't done soldering before, there'll be a tutorial at the beginning of the lab. Just let Mark or myself know. I'm not sure which room he's running it in yet. We can sort of ask him right away. And there'll be soldering stations throughout the room. So if you have solder, you can use the soldering stations. If not, you can do the tutorial, and there'll be 2 TAs around to help you and myself to help you sort of get this all working. Once you have the H-bridge, is there a question? Okay, once you have the H-bridge, you're basically just going to input various signals to it and observe the motor. You're also going to input a pulse width modulation signal, which will be done from the lab generators. So if you haven't used those before, we can sort of show you how to do that, or you can ask people. Yeah, so that's sort of it. And if you want, as mentioned, I have a quick reference for the lab. I'll put them 2 spots up here. So this is just some of the stuff you'll need, as well as the assignment. Again, the assignment has some incorrect units, so I'll upload a fixed one, but it should make sense. All right.